So we've learned how atoms have atomic orbitals that their electrons reside in at different energy levels and that have different shapes, which we know are a result of the probability densities of where those electrons will be found around the atom. But those atomic orbitals are only true for a single atom. When atoms start bonding together and forming covalent bonds, those atomic orbitals don't necessarily have the same shape. So let's take an example. If we have methane, CH4, and we were just talking about the valence electrons of carbon, and we wanted to draw an electron energy diagram for carbon. Well, we know that carbon has 4 valence electrons, okay? And we know that it has 2 electrons in the first energy level. So the energy diagram, this would be a 1s. It would have 2 electrons in the 1s. Then it would have 2 electrons in the 2s. And then it would have 2 electrons in the 2p orbital. So based on the atomic orbitals of methane, we see that there are only 2 electrons, 2 valence electrons available for bonding in an atom of carbon in its ground state. However, what's interesting in reality is the molecule CH2, which would be formed if only 2 electrons could bond to another atom, 2 hydrogens, is very unstable. This molecule can be made, but it's very unstable. Even though what we know about atomic orbitals predicts that that should be a very stable structure, because there's 2 valence electrons available for bonding in CH4. But what we do know, okay, is that there are 4 bonds that carbon can form with hydrogen, and that methane is an incredibly stable molecule. So what this is saying is there must be 4 unpaired electrons, in 4 different subshells that are available for bonding with hydrogen. Well, how can we do that? How can these electrons from this 2s orbital and from this 2p orbital be spread out? Well, the result is something called hybrid orbitals. Hybrid orbitals. Hybrid orbitals are atomic orbitals which are created when 2 or more different non-equivalent orbitals of the same atom combine. So what I mean by that is when 2 different non-equivalent orbitals would be like an s and a p orbital when they combine. So hybrid orbitals, a mixture of 2 different orbitals of 2 different energies. Okay? In fact, this is the reason this was developed was because it was the only thing that explained what we would actually see. What we know from Lewis structures and from atomic orbitals does not explain the structure of methane existing in its 3-dimensional shape that we learned from Vesper theory with 109.5 degree bond angles. And it doesn't explain that there could be 4 hydrogen bonds. Okay? So how does this actually work? Well, let's look at this diagram. Here we have, let's pretend this is for around carbon still. Here's the 2s orbital. Here's one of the 2p's, another 2p, and another 2p. We know that these are the shapes. These represent the electron densities of these atomic orbitals if carbon was by itself. Okay. What's actually happening, now that we know, in CH4, in methane, is that carbon is forming 4 equivalent bonds to 4 atoms of hydrogen. So since it's forming 4 equivalent bonds, we must have 4 equivalent hybrid orbitals. And in fact, what we get when we mix the 2s and the 3 2p orbitals is we get what are called sp3 orbitals. And we make 4 of them. 4 of them because we can form 4 bonds with carbon. So you can see when we look at the electron densities of these, each one of these hybrid orbitals have the same shape. The only thing that's different is their arrangement around the XYZ axis. Okay? And as you can kind of tell, they look kind of like a blend between the dumbbell-shaped p orbital and the spherical s orbital. They're just kind of elongated on one side and shorter on the other side. And then if these are all arranged around a central axis, what we get is a three-dimensional structure that looks like this. And now from our VSEPR theory, we should see that this looks very, very familiar to what we've built with our models and represents the tetrahedral structure that methane has, with the bond angle between between every bond of 109.5 degrees. So hybridization is a theory. The idea of hybridization is the theory that explains why certain bond angles and why certain molecules exist. Atomic orbitals would not be able to explain that alone. Let's talk about another example. Okay, NH3, ammonia. Okay, if we drew the electron energy diagram for ammonia, okay, we know nitrogen has 7 total electrons, 5 valence. So 1s, and the 2s, 4, and then in the 2p, it would have electrons like so. But we know ammonia, if we figure out the molecular geometry of ammonia, is that ammonia also has a tetrahedral shape. Ammonia is tetrahedral. Well, how does that work? What's going on? Well, first, let's look at the Lewis structure. So here's what the Lewis structure for ammonia would look like. Okay, with that one lone pair at the top. So this is saying there's kind of 4 electron groups, 1, 2, 3, 4, on ammonia. Okay, but this doesn't necessarily explain, this energy diagram here doesn't necessarily explain that phenomenon. So what must be happening is we must be having hybridization. We must be having sp hybridization. More specifically, we're also forming sp3 hybrid orbitals. So if we drew a new energy diagram that shows these orbitals hybridized, we would still have the 1s down here. It's too close to the nucleus to be involved in bonding. And what we're getting is the sp3 orbitals, which we now have 4 equivalent ones of equivalent energy. So these 5 electrons, these valence electrons for nitrogen, are now distributed like so. 1, 2, 3, 4, and 5. And now this fits with what we would expect to see in the Lewis structure. We have 3 electrons that are available for bonding with hydrogen, okay, just like here. And we have this lone pair that's not available for bonding but still around the hydrogen, which we see up here. So what we're kind of starting to see is now theory is starting to fit with experiment. What you need to be able to walk away with today from this video is what the idea of hybridization is, the definition of a hybrid orbital. Okay? You need to know the reasoning behind why this structure alone, this energy diagram, doesn't explain why methane exists. And you need to know how that alters the electron energy diagram, as shown down here, why ammonia goes from these 1s, 2s, 2p to these hybridized orbitals that are at equivalent energies. And tomorrow in class we'll talk about sp hybridization, we'll talk about sp2 hybridization, we'll talk about a variety of sp3d, sp3d2, and see how all of these help explain what we've learned about VSEPR theory.